Hello, we are Team 22044, and today we will be presenting our project, which is a hyperspectral imager. Our sponsor is Raytheon Technologies, and our mentor is Lee. I'm Allie Harkins, I'm in engineering management, and I'm the team lead. Sehrish, Choudhary, and Dattilo are the electrical and computer engineers on the team, and Avalon, McLeod, and Kevin Mayer are the optical engineers on the team. Hyperspectral imaging captures images at different wavelengths in order to identify different features of a scene by their spectral signature. Current industry standard hyperspectral imagers are very costly and require complex design. Raytheon Technologies has tasked our team with developing a practical and low-cost solution. The scope of our project is to create a hyperspectral imager that is able to distinguish between the spectral emissions of a red, green, and blue LED. In addition, we set an objective goal to apply the device to use cases such as identifying fake currency and analyzing food quality. Typical cameras use a refractive lens. This lens intakes white light and focuses the light to one spot on the optical axis. Our hyperspectral imager uses a diffractive Fresnel lens to intake white light and chromatically separates the different wavelengths to different positions on the optical axis, called the focal planes. Our system then translates along the optical axis, focusing on each focal plane. The system uses an image processing software that synchronizes the focal plane position to the wavelength in focus. Here you can see red is in focus first, then green is in focus, and lastly blue is now in focus.
Our functional requirements were developed by our team and sponsor to be the following. The system shall separate light, detect image data through focus positions, synchronize with the focus motor, perform post-processing of images, and allow for user interaction. These define the basic architecture of the system, containing an imaging and detection system, hardware controller, data processing software, and user interface. The system block diagram describes the interactions between each of these subsystems. Light from the object is collected by the imaging system, which separates it into wavelength-dependent image planes. The detection system, controlled by the hardware controller, is able to record these images at known wavelength plane locations, which sends them to the image processing code. After the image data has been processed, the spectrum of a selected region of interest is shown to the user. The imaging system consists of a diffractive lens and a Cox lens. The system requirements were largely motivated by ease of image processing. The more important requirements are highlighted here. The f-number limit of the system ensures that the depth of focus is small to increase wavelength resolution. Our system is made to be image space telecentric so that objects in a scene don't move locations on the detector through focus. These two videos show the difference between a telecentric and non-telecentric system. The efficiency requirement of the diffractive lens ensures that the intensity into the first order of diffraction was optimized and was done using a blaze diffractive Fresnel lens. The Cox lens is an unmounted triplet lens to give us maneuverability in the lens tube design. Proper ray tracing and simulation was performed in ZMAX to ensure that all requirements would be met and to allow for preliminary image processing with simulated images. Our detection system involves a monochrome detector mounted to a translation stage. The detector was selected based on field of view considerations and responsivity to light within the 400 and 900 nanometer range. A minimum stroke distance for the stage was set based on necessary chromatic separation and different object distances for our use cases. These two items were decided upon by doing a trade study incorporating factors of cost, schedule, and performance weighted appropriately to the project's constraints. The winners of the trade study were the Fuyu FSL30 linear guide rail and Allied Vision camera.
The hardware controller is required to accurately move the stage to each image location and was chosen to be applied for ease of integration with the stage and processing code. A Gaussian imaging equation was derived from the system to integrate wavelength location to the controller. The image processing software is required to output the spectrum of objects in a scene captured by the detection system. For our proof of concept, our scene includes a red, green, and blue LED. Detection indicates knowing the peak wavelength location and the line shape of the spectrum. To do this, the image processing software records the focus measure as a function of wavelength using a focus measure algorithm at a selected region of interest. For each wavelength-dependent image, the focus measure is a direct result of what wavelengths are present. The user interface is coded in Python for ease of integration. User interactions involve selecting what wavelength range to look at and corresponding step size, calibration of the detector, and when to start and stop the image capture. The user is able to select the region of interest, and once the image processing software has processed that section of the image, the spectrum is presented to the user. The housing system was an objective goal to make the system portable and consisted of the camera box and lens tube. These elements were given restrictions based on the ability to be handheld, largely affecting its maximum size and weight.
In order to verify that we meet all the requirements for our system, we defined preliminary and final test procedures along with a test slowdown involving each subsystem of our HSI. For our final testing, we tested the imaging system and the hardware controller in parallel since these subsystems are independent of one another. The remaining requirements were tested with the fully integrated system, as proving the functionality of some systems required this. Here, we are performing our tests on the imaging system in the lab. One of the most important requirements we had for our imager was efficiency, which we tested using several narrowband filters and transmission of a broadband white light source. We verified all other design parameters using optical testing tools such as an ocean optic spectrometer, calipers, and data processing. One major issue we ran into during the integration process was acquiring the diffractive Fresnel lens. The original manufacturers hired to make the design were unable to do so. So one of our optical team members went through the training required to make a binary prototype and final calibrated grayscale DFL. This process involved both binary and grayscale maskless lithography, fused silica plasma etching for the binary prototype, and UV resin cured stamping for the grayscale optic.
Next up, we will talk about our hardware control. What we really needed to achieve here was accurately and precisely moving the stage such that it could ultimately be integrated with the derived Gaussian imaging equation. This involved writing and testing software that directs the motor driver to move the stage, taking data on where the stage moved and then modifying the code such that we can map distances and positions to the motor steps that move the stage. This is the detector purchased from Thor Labs that we will use to capture images as we move along the optical axis. Most of its requirements are verified through its datasheet specifications. However, its most important requirement with regards to integration is making sure that it is aligned on the optical axis with plus or minus 25 pixels in the X or Y direction. With all of these subsystems tested, we were then able to take images over a 400 to 900 nanometer wavelength range with a red, green, and blue LED within the HSI's field of view. A combined image shows the best focus of each LED overlaid onto one image. Our image processing software then generates graphs using the modeled focus metric algorithm at a given wavelength. Here is a comparison of our HSI-generated intensity versus wavelength plot to that found with an Ocean's Optics spectrometer. At this point in the integration, we were accurately measuring the peak wavelength of each LED, as well as each LED's full spectrum, with a resulting correlation coefficient above 0.9. Our user interface is integrated to allow user control of the image processing, hardware controller, and detection systems. The translator control interface allows for manual movement of the stage for calibration or specific wavelength image viewing. The detector control interface allows the user to begin imaging a range of wavelengths in the scene after calibration. Lastly, the data output display shows the combined image and spectrum resulting from image capture.
After all modeling, analysis, testing, and integration, we were able to produce a prototype hyperspectral imager that met all requirements outlined by our team and our sponsor. The threshold goal to image a red, green, and blue LED was achieved while furthermore being able to prove our objective goals of making the system fully enclosed in housing and being able to identify fake currency.
Through this capstone project, our team has learned an incredible amount. We encountered many challenges often faced in industry, including difficulties to schedule and budget, communicating our progress with our customer, and most importantly, learning how to work with an interdisciplinary team to successfully create a desired product. Our issues with procuring the dispersive component of our system gave us insight into the iterative collaboration process needed to develop a repeatable manufacturing process and taught us a lot about the difference between design and fabrication. Thank you for watching our video, and we look forward to seeing you on Design Day.